Hello, everybody, and welcome to our Future in Space Hangout, where every other week on Thursdays we check in with various astronomers, engineers, and space technologists to learn about the projects being developed for humanity's future in the exploration and understanding of outer space. My name's Tony Darnell from deepastronomy.space, and today's topic is ISRU, or in-situ resource utilization. And if you don't know what that is, it's all right. It's all about using what's out there already in space, on Mars, on the moon, wherever we go, to help us inhabit and colonize space. It's much easier to use what's there than to try to schlep it all with us. That's a term my grandmother used to say. She always schlepped things around. And so people have been looking at what resources we could use that's already out there to make the task of exploring space easier. And for decades now, NASA has been addressing or assessing options to use these resources that are available in space, mostly on the moon and Mars, to sustain long-duration human operations. And it would be prohibitively expensive to send from Earth to either of those places enough resources for astronauts to carry out priority mission goals. So, not to mention all the stuff about settling there. So NASA's human spaceflight program focuses on lunar operations and technologies to enable eventual human missions to Mars and all these other places, and it's become a high priority. ISRU has become a high priority in NASA's technology investment plans. So today we are going to be talking with scientists from NASA's Johnson Space Flight. I keep doing that. It's NASA's Johnson Space Center. You got rid of the flight now, to help us get a grip on what's being done in this area. And I want to say first that these hangouts are sponsored by the American Astronautical Society, or Association, American Astronomical Society, whose members provide our vanguard for space travel and space astronomy. And I want to thank them for their generous support of these hangouts, without which we could not bring them to you. So thank you very much for that. Okay, since we are live, we're also taking your questions and comments on YouTube, Twitch, Facebook, and Periscope. So we hope you'll use this time to ask questions live. But if you're watching the VOD of this broadcast, or if you're listening to the audio on the podcast form, don't let that stop you. You can still comment as well and leave comments and questions, because I follow all of our Hangout comments even after we're done broadcasting. So feel free if you're watching this after the fact. Okay, so let me bring up my co-host, Dr. Harley Thronson. He is from NASA's Goddard Space Flight Center. Hi, Harley. How are you doing?
Doing well. Good afternoon.
Good. It's good to see you.
Nice to see you. Well.
And it's been a while, but gosh, when did we last do a Hangout? It was November, beginning of November.
Yeah, sorry, it was October. We took
That's right.
I can't explain. We took November off.
Right, we sort of did. Okay, well, why don't you introduce our topic a little bit more than what I just did, and maybe talk a little bit about thank the American Astronautical Society as well.
Yep. Although it was an excellent introduction. So thank you, Tony.
Yeah.
You got it exactly right. The experience so far with human spaceflight has been that the astronauts have not really much taken advantage of the resources that exist in space. The space station, of course, decades ago with the Apollo program, everything that they needed, eating, drinking, they took with them, and that is extremely expensive. So for several decades, NASA, other space agencies as well, NASA in partnership with academia and industry has been looking at ways of exploiting the resources that exist in space. With the new direction to NASA to develop scenarios, architectures, and the technology for operating on the moon within the next, say, 10 to 15 years, the interest in ISRU on the moon has increased significantly. In addition to the value of supporting astronauts on the surface of the moon, for that purpose alone, the moon has been identified by NASA as a stepping stone eventually to Mars. So developing, if I could say, developing the ability to use the resources of the moon both for has got two purposes: to allow operations on the surface of the moon, exploration and so on, and then eventually to enable humans to go to Mars. Jerry and Steve, our guests today, have been part of a series of workshops on.
Is that you?
Yeah. I thought I turned it off. I guess with an iPhone, off does not really mean off in the human sense. And Siri seems to have taken over my iPhone. In any case, I have been involved in a series of workshops, most recently this past August, in which at that workshop, we technically, critically examined claims that operations and technologies, capabilities being developed on the moon to enable eventual human missions to Mars. We examined those claims critically, including ISRU, and found, there were some real possibilities that properly exploited resources on the moon not only would support human operations on the moon, but would also allow us to travel with humans eventually to Mars. Got a couple of experts today, and I think it's time to introduce them.
Okay. Yes. So here I have everybody up now, and we are right next to me on my panel here is Stephen Hoffman. Both of these guys, by the way, are from NASA's Johnson Space Center, and we are. So Stephen Hoffman is working on ISRU there at NASA Johnson. Also, right below me is Jerry Sanders, who is also working on the same topic. So welcome, guys. And please let me know who wants to give us an overview about what NASA is currently working on. Well, actually, let's take a step back. Both Harley and I have given a brief introduction to what ISRU is, some of the challenges, but I guess would you tell us what NASA is most concerned about with this topic as far as human exploration and what resources they're putting towards this problem?
You may take a stab at it, Jerry.
Yeah, sounds good.
Okay, go ahead.
In this realm, I'm I am one of the mission planners. I'm the guy that tries to take all the pieces that you need to make a mission work and put them together in a way that makes sense, and try not to leave anything out. If I can define for Jerry what he does, he is more centered on certain pieces of technology that I like to put into my equipment basket of things to take along to help pull these missions off successfully. And as you mentioned, ISRU, I guess I most hear about ISRU in the sense of making propellants somewhere, but I tend to think of ISRU in a more general sense, more broadly applied, in that it's using anything that you find at a destination to help you pull off that mission successfully and help you avoid bringing something along that you might otherwise consider necessary. Up to this point in time, all of our missions to the moon, to low Earth orbit, other than sunlight for power, I guess, we've tended to bring everything along with us, and that means every pound or every kilogram of something we need to bring along means it's a pound or a kilogram of something we can't do otherwise. So propellants is a very good example. Breathing gases is another good example, but you can broaden that out to, you can think of construction. If we needed to build up berms or even full habitat structures from local materials, that helps us avoid having to bring all that mass along with us, and instead allows us to either come with less stuff, which means smaller launch vehicles, or with the same launch vehicle, we could actually bring more equipment that you're not going to be able to find there, and have a more extensive or more effective mission in the end. So with that, that's kind of my role in life, is to try and figure out how do we try and leverage the stuff that's already there, so we don't have to bring it along, And Jerry helps us figure out how to take raw materials that are there and turn them into something that's useful.
Okay, Jerry, you want to give us a little idea about what you're working on then?
Well, Steve gave a great overview, and as he pointed out, using the resources versus bringing things from Earth is very important. One of the things to kind of factor into that Steve was alluding to, that I can expand upon just slightly, is the fact that for every kilogram that you land or bring to a planetary surface, again, whatever it might be, requires, propulsion systems and landers and transfer stages and such, to the extent that if you work backwards, it equates to something on the order of 7.5 to, say, 11 kilograms of stuff that actually has to be flown into orbit from the Earth's surface. So, propellants obviously has a huge factor. Typically, it's 75 to 80% of the spacecraft's mass, if not more. And in the case of Mars, for example, it takes something on the order of about 30 metric tons of propellant to get off the Mars surface. So when you multiply that by 7.5 to 11, and what's needed to actually deliver that ascent propellant, you're talking about 3 to 5 SLS launches. So obviously, propellants is one of the first ones that we look at, and so as Steve was alluding to, my job is how to figure out how to make that, and Steve's job, to a certain extent, is how can that be used in the architecture. Besides propellants, some of the other things that we look at is how do we reduce mission risk to the crew. So again, if you have to bring everything from Earth and you just didn't bring the right amount of material with you, or the right spare part, or you ran out of something, the current approach is you have to bring it, wait for the next resupply mission, for the space station and next, cargo mission. Well, if you can make things on a planetary surface, Moon or Mars, versus having to wait, that also helps you tremendously. Maybe it's that spare part that keeps your life support system going, or it's extra oxygen to do more EVAs. So we're basically looking at, well, what are the resources out there? I think one of the charts that I have kind of shows in general the things that we're looking at.
Okay, hang on just a sec. Let me get my cursor back. While I'm searching,
chart 3, but
chart 3 on okay, and let me.
So we look at what are the resources that are there.
Okay, it's up now.
And water is obviously one of those that we find, hopefully at different locations, that has tremendous amounts of usage, radiation shielding, drinking, making propellants. Oxygen sources and is probably the next biggest one, for breathing air and for propulsion and for life support systems. And then, carbon and metals. So how do we, first of all, do we know everything about these resources that we can? Then the next thing is designing hardware to extract and excavate and process those resources to get you the products that you want.
Now, Jerry, isn't it true that the moon was recently, I think, if I'm remembering my press releases right, and I may not be remembering them right, that the moon has a lot more water than we thought it did, doesn't it?
Yes.
So,
originally for Apollo, and post-Apollo, when we had samples, the thought was the moon was pretty bone dry.
Right.
There were those that had theorized that the poles at the moons, in permanently shadowed craters, might have water there, but nobody really had any evidence. It wasn't until Clementine, I believe, flew with a synthetic aperture radar, and then subsequent missions like Lunar Prospector, eventually the lunar resource lunar reconnaissance orbiter, that we started learning more and more that water may be pretty prevalent at the poles, as well as migrating across the surface.
Okay. So this is sort of listing all of the different major components that are important for doing any kind of in situ resource utilization. And so this water being very important, it's very heavy. It's nice to have it already there if you can use it. But with it, you can make all kinds of other things out of it, not just drink it. So that's really good. And of course, the other ones you've listed here are also important. But this reminds me, let me go ahead and get to a related question that I saw from Hans. I think it was Hans Milling. Where did it go? Shoot, it scrolled past. Oh, it was Upcycle Electronics. He wants to know, in what level of in situ industrial processing are we talking about here? Are we talking smelting and refining, or base materials like metals? We're kind of talking about both, right? Stephen, on the one hand, finds these things, and then Jerry, you do stuff with them, right?
Well, I mean, yeah, we're just like everything that goes on. You start with the most basic of products, the most basic of processing systems. So smelting, getting raw materials for manufacturing, maybe making simple plastics like ethylene or polyethylene, because it's fairly easy to do. As starting points. Eventually, as time goes on, we'll refine things more and more, but there's always this balancing act in terms of, how much infrastructure do you need to get the product versus how much product you actually need to produce. Mm-hmm. That's the other reason why propellants typically are considered, early on, is because I need, typically multiple metric tons of product. The infrastructure I need to generate those can be 1/10 of the amount, compared to it. So I get a lot of bang for the buck. Whereas if I'm making electronic parts, what's the machinery needed to do that versus just bringing spare chips along. So that's kind of how we think about these things.
Okay. Let me just...
If I could, you said
you
Steve finds it. I don't really find it. I use what Jerry's going to produce. But finding it is an important part of the problem, too, because there's not water everywhere on the moon, for example. There's not water everywhere on Mars, either. You have to know where it is, and you have to know... You get into the fine... I don't really find it. I use what Jerry... I know it's kind of there, but what state is it in? What's the quality of it? How much unusable stuff is mixed in with it that I got to separate out? Those sort of questions come into play. So there's an intermediate step between knowing it's there and turning it into something that's useful. Now, on Mars missions, where I have more experience than lunar stuff, although I've worked both, we kind of broke the paradigm of bringing everything with us in the most recent series of design reference missions or design reference architectures, where we actually got NASA, which tends to be a fairly conservative organization when it comes to crews and putting crews at risk. We broke the paradigm by saying that we're going to make at least part of our propellant on Mars. And we justified that by saying we're going to make oxygen, which turned out to be about 80% of the propellant we needed to get off the surface, by cracking the atmosphere. And the reason we could get away with that is because we knew where the atmosphere was, we knew what it was made of, we knew what the concentrations were. So it was a fairly easy argument to say, here's my raw material, and here's the machinery that Jerry was talking about. Here's the machinery I need to turn that atmosphere into the oxidizer I need for my ascent vehicle to get off the ground. So there is this balancing point, as Jerry was mentioned, that you have to look at the how much stuff am I getting off the back end of the ISRU process versus how much stuff do I have to bring to make it to begin with. And if I have to bring more mass with me to make it than I get by making whatever it is you're making, then it isn't really paying off. You need to have it the equation go the other direction, where I'm bringing just a little bit along to make a lot, and then you can start getting a lot of leverage all the way back to launching less stuff, as Jerry mentioned earlier in this discussion.
Right, and well, I get the part about the being able, you want to launch and send less stuff than you actually end up making there. That's where you get the benefit. But I don't know that you said that NASA's kind of conservative. I don't know that it's conservative to want to bring everything with you. That's really kind of a risk, I would think, isn't it? I mean, you kind of want to make sure that you're using stuff that's already there. That would be the conservative approach, in my opinion, isn't it? I mean, it's not really all that conservative to just bring what it's not even practical. You can't even really do it.
The conservative part of that is knowing what you are, if you're going to rely on something, making something at your destination, and you're putting the crew's life at risk in doing so, you better be pretty sure that what you're making it from is really there and really in the concentrations that you think it's there, and that the process itself, which can break down, can work reliably enough or can be repaired by the crew easily enough that you're not adding additional risk to the crew by introducing this another step of utilizing something that's already there, compared to bringing everything with you that you can test on Earth and make sure everything works the way you want it to work on Earth before you ever leave.
Okay, well, to what extent then are we dealing with the in your equation of when it becomes worth it? And this is, I guess, to both of you, but is part of the plan to send things ahead of time, like, I don't know, robotic miners, mining equipment and maybe 3D printers?
Yes.
So you send that first, get it out there and work. I was watching a show. What was it? Oh, I think it was The First on Hulu. About going to Mars. Have you guys seen that show? And
No.
one of the things they did in the show, it was a really good show, really good. It's about first trip to Mars, or first mission to Mars. And of course, they had to send habitats there that already worked. And one of the big tense scenes in the show was that they weren't getting any feedback from one of their labs that they had already sent out ahead of time, and they didn't want to send a crew out there without knowing that lab worked. So this is kind of that way, where you're sending out equipment. And is that the plan? Is that to send things out to the moon or to Mars first, get it working, and then send people there?
Yeah, that's pretty much the way it is, and that's as Steve was mentioning, to break the cycle of conservatism about having ISRU in a critical path for the crew. We typically take two approaches. One is to fly demonstrations early on of whatever concept we think we are going to use in the human mission. So, for example, the Mars 2020 mission will actually have a small demonstration of ISRU called MOXIE, where it has a compressor to suck up the Mars atmosphere and a solid oxide electrolyzer device to crack the carbon dioxide in the Mars atmosphere into pure oxygen.
Okay.
And so that will be tested on that mission. Now, yes, it's 1/100th scale of what we would fly on a human mission, but it shows that it's doable.
What's the timeline for that?
It launched in 2020.
Oh, good. So it's imminent. That's awesome.
But you're correct. The other thing that the approach we've taken that goes back to, I think, Mars DRA 3.0 at least, if not earlier, was the idea that you send your plant and your ascent vehicle, ahead of the crew, typically one opportunity, 26 months. It lands on Mars. It completely refuels the vehicle before the crew either ever leaves Earth or ever descends down to the Mars surface. So we know the product's there. We know it's ready to be used. And so there is no risk to crew or mission at that point. So what Steve is helping with at the moment, for example, is if we do a lunar mission, lunar lander, could we use oxygen from the regolith on the moon or oxygen and hydrogen from water for a future mission to either take the crew off or hop to another location. And that would require us basically to demonstrate and have that product available before that mission occurs.
Is it easier? This may seem like an obvious question, but I don't think it is. Is it easier to do this stuff on the moon or to Mars? Because the reason is, to me, not obvious is it might be harder to do all this on the moon because there isn't any atmosphere, first of all, and the resources are probably not as they're probably different enough that you really aren't going to get much out of using that technology to go to Mars. Are you? So is it easier to do these in-situ resource utilization projects on the moon or on Mars?
It's a little of both. I think you hit one nail on the head, and that is, the Mars atmosphere. As Steve alluded to, Mars has an atmosphere that I can acquire anywhere on the surface. It's a gas, and gases are easy to collect and process.
Right.
The Mars surface environment is typically much more benign, depending on where you land. Yes, there's day-night cycles, there's yearly cycles, but you can find locations that aren't too extreme in temperatures. And having an atmosphere means your thermal control systems also are relatively more benign than the moon. The benefit of being on the moon is the short time delay.
Yeah.
So if we're pre-deploying all of this hardware before the crew shows up, and we have communication time delays of 8 to 40 some odd minutes, that makes controlling that hardware very difficult.
Yeah.
And so that's where the moon definitely comes into play as being easier.
Do you have any comment on this? Go ahead, Steve.
Tony, if I could, there's another piece of that too, though, that most people, it's obvious when you think about it, but it doesn't really float to the top. And that's it. In any of these ISRU, well, I'm going to go back to my original statement. Any of these propellant-producing processes, if you think about it as an end-to-end process, some of the back-end parts of this, the downstream parts of this, will be common for the moon or Mars. Once I have oxygen, I have to liquefy that oxygen. I have to put it in a tank. I have to keep it cold with cryogenic coolers of some sort. I have to transfer it from one tank to another. Those parts of the propellant production process don't care whether you're on the moon or Mars. It's the front end where you have the raw material that's coming into your processor where you have some differences. And on Mars, there's an atmosphere to work with. That's one thing. But we also look at minerals that are on the ground that have the chemicals either chemically bound in the minerals that we want to get, or simply stuck together. If you think about water in clays, there's water there, but it's not chemically bound to the rock. It's just there. So whatever the raw material is that's coming into the front end of your processor will define some of the unique aspects of this propellant production device system. But the back end could look very similar to on either one of the planets. So if I can do some of this stuff on the moon, I may learn 50%, 60% of what I need to make it work on Mars too. It's just that the front end of what I'm feeding this processor will be different in some respects on either of those two planets.
Yeah, and I think Harley was alluding to that fact that the workshop in August and subsequent discussions we've had on, what parts of lunar ISRU, whether it's operations, whether it's individual technologies, whether it's resources, how similar are they to processes that we would do on Mars, and how would that buy down those risks? And so there is a lot of similarities that can be leveraged.
Okay, right now, getting a lot of news on OSIRIS-REx. It's at Bennu now, and it's NASA's mission to an asteroid. Are you expecting to learn much that's going to help you when with regard to resources in the solar system? Is this something you're excited about? Are you expecting to get some good data on what kinds of raw materials might be available?
Oh, tremendously. Both Hayabusa 2 from the Japanese,
Right.
as well as Osiris Rex. We learned a tremendous amount from the Dawn mission.
Oh, that's right. Dawn recently ended the mission. That mission.
So, I mean, between those three, and then also you can think of the European Comet mission that was recently successful as well. So yes, how that plays into our long-term plans obviously is still
it's not going to really. Yeah, are asteroids going to help much with Mars and Moon? And
not I mean,
really.
There is the possibility that Phobos and Deimos are Class D type asteroids and may have similar mineral and water characteristics associated with them. So anything that we learn about asteroids might be applicable to
those
eventual use of Mars's moons. But here again, when you look at what NASA is focusing on, especially for Mars, it's the surface resources and usage that comes to mind first.
Okay.
The asteroids are going to have the kinds of raw materials that could potentially be useful, but then you have to start factoring in the transportation costs. And that's where it tends not to work in your favor, at least for, say, lunar missions or Mars missions, because of the amount of time and propellant you need to go all the way to an asteroid and make whatever it is you're going to make, and then the time and propellant to get all the way back to where you're going to use it. So a rule of thumb, it's not a formula, it's not an equation, but a rule of thumb for ISRU is the closer you are to where you're making it, the better advantage you get from it. So if I have to go a long ways to get to something, a long way to bring it back, it tends to lose its benefit to a mission.
Well, that's true here on Earth. I live in Florida, and I still cannot believe that when I buy oranges, I'm buying California oranges. I just don't know. I don't know. To this day, I can't understand it, but I am, and I'm getting avocados from Mexico. So it's weird, but you're right. That's true everywhere, and it's, I guess, this is really long-term asteroids, right?
Well, let me add to what Steve just mentioned about asteroids and about products and such. Mm-hmm. One of the things that we have been talking about up to this point has been, how is ISRU fitting into NASA's missions? The Space Policy Directive 1,
that sounds important.
Current administration talks about how do we leverage space and how do we commercialize space. And besides NASA, there may be other users, and asteroids may be one of those that, while it obviously would be difficult to plan a NASA mission to Mars, say, using asteroidal resources because of the amount of time taken to deliver the resources from the asteroid to say, cislunar space. A business plan that builds up around the idea of industrializing cislunar space could make that argument. So going back to your question about the interest of asteroids, I look at it from two perspectives. One is, how relevant it is to a future NASA mission, but the other is how relevant is the work that we're doing also towards SPD-1.
And so okay, so the policy directives that NASA is currently operating on, I don't know what everything that it says. In fact, I don't know anything it says, but this is just how it can use what it's doing to commercial benefit, as well as what it does with its own missions, right? Am I hearing that right?
Yeah. Well, I mean, there's basically, I don't have the policy.
Yeah, we don't have to go into it. I don't want to really get into it.
It's not that prescriptive, Tony. It's.
Am I not surprised?
But it does call out the fact that NASA should be helping to promote or foster more commercial activity in space. So
Okay, sure.
to the degree that NASA can help move things along, that's within NASA's purview or NASA's direction to make that happen.
Okay.
And I think the commercial lunar lander program, for example, is a good example of how NASA is trying to, take the spirit of that and apply it, where instead of NASA necessarily building designing all these small landers, turning to commercial folks and saying, okay, just like the cargo delivery to space station now, if I have a payload that needs to go to the moon, who can fly it for the cheapest amount of money?
Yeah, there's other side effects. Though I just found out that the SpaceX Dragon capsules are contaminating the ISS with some of their experiments. So that's another hangout topic. But I want to talk a little bit about the gateway, because we did a hangout on it a while back, Harley and I, and that's another thing that NASA is highly emphasizing right now is this cislunar station gateway that is a stepping stone to other places like the moon and Mars and they're very excited about it. Now, when I first heard about it, I was enthusiastic. I thought, well, this is great. But then after the hangout, I started to get these people were really annoyed by the idea of the gateway. And I looked into it a little more, and I guess there's people who just think we should just go to the moon and forget about this gateway business. But let me, in the context of our hangout and our topic of ISRU, is that going to be a factor in what we do on the moon with developing resources on the moon? Because it seems to me like you could use this gateway to put stuff in, right? You go down to the moon, you make stuff, you put it up in the gateway, and you can send stuff anywhere you want in the solar system. Is that a part of your thinking on any of this, or is it not a part of your thinking? The gateway.
Well, Steve, do you want to take it, or do you want me to?
I'll start, and you can jump on.
Okay.
The gateway. I guess maybe, and take this as personal opinion. I view the gateway as somewhat neutral in that respect. In that, if it's there are things that we can do with it that we couldn't otherwise do. If it's not there, it doesn't mean that you can't get to the moon anymore. So it has advantages for both lunar and Mars kinds of missions. For the Mars missions, something that's not quite obvious is that we'd like to reuse the vehicle that takes crews to Mars and back. In prior years, when there was no there, we tended to dispose of those vehicles after every mission. If there is a there in the sense of something orbiting around the moon that can provide some level of housekeeping support, think of it as a garage or a Tesla plug-in station kind of a thing, then we can afford to bring those transfer vehicles back into a lunar orbit and leave them there, refurbish them there, and then reuse them. But if Gateway isn't there for whatever reason, then it doesn't stop us from going to Mars. It doesn't stop us from going to the moon.
Yeah,
it's something that just has to play with the rest of the pieces that you're putting together.
To play nice with everybody else. Yeah. Okay. Do you have anything to add to that, Jerry?
Well, yeah. Steve and I have been with NASA long enough that we've seen a lot of different architectures. And with respect to the moon, it boils down to which particular transportation approach do you want to use. Apollo had a low lunar rendezvous with its lander and crew with direct launch from Earth. There's been approaches where, for example, I think the Russians were looking at having all their hardware meet up in Earth orbit before going to the moon. The Gateway gives an interesting approach in the fact that you can separate your kind of up down from the moon to a neutral point with the delivery of cargo from the Earth's surface. and looking at the changes in velocity needed for going down to the surface from a gateway versus delivering hardware from Earth orbit to the gateway. You can break up your transportation system in a different way than you would otherwise. I think Altair lander was a good example of trying to do a direct descent to the lunar surface from an Earth launch vehicle, and you could see how big it was. It was like 3 or 4 stories tall for the descent stage. So having an intermediate point like a gateway could allow you to have smaller spacecraft and multiple elements that can be reused differently. As Steve said, you don't necessarily need it to go to the lunar surface, but it opens up different opportunities.
So now let me guys add one more thing in the context of this ISRU discussion. If we have a gateway, and the gateway, you can think of that in a broader sense. It doesn't have to be the gateway we're talking about now, but a station nearer to the moon. We could park a lander vehicle there, for example, and just bring propellants. And those propellants could come from the lunar surface. They could come from Earth. But it saves us, in that respect, it saves us from having to bring that lander every time we want to send a crew to the surface all the way from Earth. We get it up there one time, and then we refuel it, we refurbish it, and it opens up, it gives you better leverage for using propellants that you make on the moon versus having to launch them from the Earth, much deeper gravity well than the moon is. And so if you're playing the long game, having something like a gateway where you can park your lander in between missions and refuel it in between missions, it gives you a reason for trying to accelerate maybe the idea of making propellants on the moon, and then using those propellants, like I said, closer to where they're being used, the better leverage you have in having them there. So the gateway in that respect could become, if you're thinking the long game again, it could be a benefit in promoting ISRU propellants that are coming from the lunar surface somewhere.
And that's the part that makes the most sense to me. You've hit it right on the head. I always thought I get people's impatience about getting to the moon. Let's get a base there. Let's get people on it. Let's start doing stuff. Let's start digging it up and making stuff. I get that. It'd be great. I'm all for it. But I also get this gateway thing. It makes a lot of sense. And you're right about the long game, and that's where it comes in. It's not helpful just to get us to the moon and to use it near the moon, but we can keep stuff up there that can go anywhere else. And we're already up in space. It is a foothold in space that is probably, I assume, because NASA is wanting to do this, more realistic than trying to build a lunar base. Now, you talk to various people around and they'll have opinion. Everybody has an opinion on this, but I don't really have, I'm agnostic about whether the gateway goes up or not, but I do see the value in it. And so I just wondered, if you guys use it in your planning at all. And it sounds like you don't really, you're going either way. You do what a lot of people at NASA do. You just, if it's there, great, we'll use it. If not, well, we're not, our mission doesn't depend on it being there. So that's.
Well, we do in our work, just to be clear, one of the definitions of ISRU is the fact that it provides a product to a customer. Mm-hmm. And so by definition, there has to be a customer that uses it. So if NASA is designing a lander that is based off of being at the gateway, then that sizes our hardware. That kind of tells us what development path we need to go down. If NASA is doing a direct, delivery of a lander from Earth, like Altair, then that changes the paradigm potentially on whether you could reuse that lander or not, and how much ISRU can factor into it. So since Gateway is a major item that is currently being pursued by NASA as a first step for both lunar and Mars exploration, then obviously what Steve and I do is heavily influenced by that decision.
Okay, I'm going to go. I want to get to some viewer questions because we're running out of time. And David Sims has just asked a really good one. He goes, "Why not build the gateway from the moon? If you're going to use the moon to make things, then why can't the gateway be the first thing made from moon stuff?" That's a great question. Can we do that? Do you know? I know you may be not involved in the gateway thing, but could you?
I mean, so there's a technical solution, and that says yes, you can make it from lunar stuff, but you get into the chicken and egg kind of question. To make stuff from lunar materials and put it into lunar orbit, yes, you can do that. But then I have to put all that stuff on the surface of the moon to make the stuff from which I'm going to make gateway. And when you start adding up all those pieces, so now I need a lander, and I need a factory. Let's just call it a factory that's going to take lunar raw materials and turn it into something that's of a quality that we can then manufacture a gateway from. And I'll have to have an ascent vehicle to bring it up from the moon and put it in lunar orbit somewhere. When you start adding up all those pieces for the benefit of what you want to use it for, it probably makes more sense to deliver it from the Earth, where you have all the infrastructure to build it, to test it, to confirm that it's going to do everything you want it to do, rather than moving all of that, moving the Kennedy Space Center, moving, pick your favorite aerospace company, moving their factory to the surface of the moon to make something there to put it into lunar orbit. If you make the assumption that all of that's already there, then yeah, it probably makes sense. But it's the getting there is currently nothing there. There's no there from which to make this stuff. So you've got to put all of that on the moon before you can talk about using lunar-derived materials to make a lunar space station.
Yeah, it does. Maybe
I think a good analogy of how we might use the moon in building future habitats and such. I worked with the Russians for a number of years, and my colleague took me out to his dacha on one trip, and he was building a really nice house out at his plot of land that had, very, very interesting, plants and fruit trees and such. But he had basically a shack that he lived in. Had a stove, it had a toilet, and it had a heater, and he lived out there on his own while he's building his big house. You can kind of look at maybe some of what we might do on the moon the same way. The early habitats are delivered from Earth. They're small cans, pre-assembled. The astronauts could live in that to build their future home. And now you can take the time and the effort to do it properly and have the people there versus trying to do it all robotically, all from scratch.
Okay, can you? I want to ask one quick question. I got to read some more here. So, if we've learned anything from projects like the James Webb Space Telescope, where technologies have to be invented in order for the mission to be a success, can you guys give me a brief statement on the technology, where we are in the technology of ISRU development? Do we have most of the technology do we need to develop most of the technology yet still that we don't know how to do these things? Where are we on our level of technological skill to be able to do this?
Well, I think if you bring up chart 11 in my package, all right, that probably would be a good discussion starting point.
Okay. Let's see.
So during Constellation, which was the last time we were talking about going to the moon, starting around 2004, I believe, was when the vision for space exploration was released by President Bush. We started a development program on a number of different areas. We looked at how do we, is there water and other interesting things in the permanently shadowed craters for resource prospecting? How do you excavate lunar regolith material and transfer it and prepare it for processing? We were very interested in extracting oxygen and metals from this regolith, so we looked at different, different techniques that could be done. Besides, Steve made a comment about, resources that exist at your location. Well, trash and crew waste is a resource. And since the moon is actually pretty carbon poor, it's a tremendous resource. So we started looking at how do you process trash and waste into usable products. Steve also mentions construction and civil engineering. We looked into how would you clear areas, level them, build berms to prevent the plumes from rocket engines from sandblasting nearby hardware. And so from around 2005 until around 2011, we did a significant amount of work on all these different techniques, 3 different oxygen extraction from regolith processes. The pictures in the chart actually show that we took hardware out to analog field sites, in particular in Hawaii, where we field tested in 2008, for example, end-to-end processes for extracting oxygen from lunar regolith using hydrogen reduction. In 2010, we did a larger test that involved what's called carbothermal reduction using methane and cracking molten lunar regolith to make oxygen. So in NASA parlance of technology readiness level, we were probably at the technology readiness level 4 or 5 for first generation hardware at a scale that was usable for early lunar human missions.
Okay, so it looks like the technology is not going to be a stopping point here for doing this kind of work.
Well, there's always issues turning engineering into final flight hardware.
Right, but we don't have to develop.
The basic premise has been shown.
Okay, right, good. Good. Okay. Well, that was my point. I wanted to know, do we have to invent stuff still? And it looks like a lot of testing has already gone on with respect to this anyway. So that's really good. Let's see. I had a couple of questions and it scrolled past again. Andrew Planet. Hi, it's good to see you again. Are there any other options than only liquefying any oxygen made on Mars? If we kept only an emergency supply, could we not just get our oxygen from plants, which can adapt to differing levels of CO2? In other words, is there any other way we can get oxygen instead of liquefying?
It's who's the customer. If your oxygen is only for crew, then getting it from plants, obviously converting the CO2 and from the astronauts and any waste that they have back into usable oxygen through chemical means or biological means are all relevant.
Good. Okay. Upcycle electronics. What if we ignore the politics of picking a destination? Okay. Where would you like to send a mission if it was up to you, based on the known availability of resources right now? So this is your opinion. If somebody said, Jerry or Stephen, where should we go? What would you guys say? Stephen, you first.
I'm agnostic between the moon and Mars. I currently prefer the moon a little bit more than Mars from the fact that it's closer and potentially easier to send hardware to. And so therefore it allows me to and NASA to develop hardware possibly at a quicker rate. Especially with the idea that we might be able to commercially launch payloads to the moon versus, waiting for a long period of time before sending something to Mars. I personally want to see humans on Mars in my lifetime. So I definitely support anything that helps us along that way as well.
So Jerry doesn't care. He just wants to go. Stephen, what about you?
Agnosticism does not mean you don't care.
Okay, it doesn't. Okay, you're indifferent, I suppose. Are you?
No, it doesn't mean he's indifferent.
Well, he gave us, let's go to both. So, I mean,
go to both. Yes.
You're equally enthusiastic. The difference between one option or the other is none. So it's indifferent. Okay. Stephen, how about you?
I'm in favor of getting people into space wherever we can get them and keeping them there. I grow frustrated with the back and forth of this year we're going to the moon and next year we're going to Mars.
We all are. We all are.
The playing the long game again, I would go to Mars because in developing the pieces that we need to do Mars missions, you get most of what you need to do a lunar mission just by doing it. So Mars, getting ready to do a Mars mission, I think is inclusive of being able to do a lunar mission if you choose to do so.
Okay, well, with that in mind, let me just say this. Harley and I did a series of Hangouts with Arnold Nicogossian from George Mason University, who literally wrote the textbook on human physiology in space. And after that series of Hangouts, I actually became quite pessimistic about human beings in space. I don't know that we can survive it. And I guess I would like all of your opinion, including you, Harley. Are you worried about this at all? Do you think this is, based on all we know about human physiology, it's not a good place for us? Can we even do this? This is an opinion, of course.
I'm sure technologically.
No, I mean biologically, can we survive it?
Biology is a tough thing. I think all the problems are solvable. I don't know how widely appreciated, how really challenging.
That's my point, Harley. I don't think people appreciate just how unhealthy it is for us to be out there.
No.
I would counter that. I think we recognize that there are challenges, and the more that we explore space with humans and have them there longer in space, the more we recognize the challenges. But there are opportunities that come out of that. You look at any exploration that has been done, whether it's, crossing the Atlantic or long, journeys at sea, or going to Antarctica, exploration is risky. And I think
but getting freezing to death in Antarctica is
open, recognizing that versus assuming that every mission is going to be 100% successful and nobody's going to get cancer and all that. I think it makes sense.
So Tony, what I'm not sure what aspect of this is causing you concern.
All of it. The entire.
People were meant to fly at 30,000 feet, yet we do it all the time. We figured out a way to do it. People weren't meant to spend months.
We don't fly at 30,000 feet for 8 months to a year. And
people weren't meant to be under the sea at several hundred meters for months at a time, and yet we do it.
So
there are ways. Yes, there are problems if you tried to do it without any sort of support. Our job is to figure out how to make it feasible with the kind of support that you need for the human being, the human body, to be able to carry this off.
Well, okay. I'm just telling you what my concerns are. I mean, going to the bottom of the sea is not the same thing as going to Mars, and there's radiation issues, there's gravity issues.
Could you do it on your own?
What?
Your concern seems to be if Tony was going to go fly to Mars right now, he'd die, and that's probably true. But if Tony had the kind of habitation, radiation protection, food growth, and
gravity,
other sort of, Mars is a good place. Mars' surface is probably a pretty good place to be.
Okay. Yeah. All right.
So the transit can be as short as 6 months. I don't see it. I know Arnold. I know who he is. I haven't spent a lot of time talking to Arnold, but we have learned how to overcome a lot of the physiological problems that were in the early parts of spaceflight.
Okay, cool.
And I am confident that we'll be able to figure out how to do it in the future.
All right. That's great. Good. Well, I'm not arguing that we don't do it. I just say I'm concerned, and I'm starting to wonder if this is going to be a very unhealthy thing in the long term for the human race to try and do on a large scale. So, okay. Well, I guess we are out of time. Unfortunately, I've got to stop it here, but, let me just point out that many of you who are watching on YouTube went to a wrong link. That's because I accidentally hit a button on my Restream console that stopped the stream and then restarted it somewhere else. My apologies on that, but you all found it, and that's great. And thank you for your questions and comments. I want to thank my guests today for joining us. These are both from NASA's Johnson Space Center, Jerry Sanders, as well as Stephen Hoffman, both from, sorry, I'm moving my things around, both from NASA Johnson Center. And I also want to thank my gravitational wave rubber ducky, the Royal Canadian Mounted Police. Yes, and Harley has one as well. So
there's Steve and Jerry, there's a story there.
Yeah, those are our mascots.
Twins, Einstein paired twins or something.
Yeah, we'll tell you. Well,
no, they're entangled. They're entangled. Okay.
Entangled, yes.
Yes. So that's why we can't do the Hangout without them. So, all right, guys. So I want to thank you guys so much for watching, and we will be back next week with Astro Coffee Hangout, where we will be talking with authors of a new book that's coming out on astronomy and Astro Coffee Hangout. We'll be talking with them next week. So join us then. And on behalf of Harley and my guests, I want to thank you all so much for watching. And as always, keep looking up.
Thank you, Tony.